Hi guys, it's Roane. Welcome back to Chem 1 BSI. Today we're going to be going over some acid-base chemistry as well as some precipitation reactions and a little bit of solubility. Let's just dive right in and we'll start talking about some Bronsted-Lowry acids and bases and the Arrhenius acid and bases, and we'll go over some similarities and differences. So the Bronsted-Lowry acids are any compound that can donate an H+. So it's literally any compound with an H on it that can come off and be donated to another molecule. Okay, so example, HCl, HF, okay, even something with more than two H's can be a Bronsted-Lowry acid. Basically, this H comes off and goes somewhere else, okay? It's donating it, and that makes the Bronsted-Lowry acid. Using the same examples, an Arrhenius acid is anything that when dissociated and dissolved in any sort of aqueous solution, you can get an H plus proton. So these two are also Arrhenius acids because if you dissolve them, you get an H plus and you get a Cl minus, and this H plus is what we're looking at. So the Bronsted-Lowry acids and the Bronsted-Lowry bases are fairly similar, right? Or the Bronsted-Lowry acids and the Arrhenius acids, are fairly similar. However, the Bronsted-Lowry bases are any compound that can accept an H proton or an H ion. Okay, one of the more common examples is an OH minus group. Okay, that can accept an H plus and turn into water. Right, you guys know that. Another group, however, is an NH3 group. Okay, NH3 can accept an H plus and turn into an H4 plus. Okay, though both of these are Bronsted-Lowry bases. Both of them can accept H plus. That's all a Bronsted-Lowry base is. Anything that can accept H plus. However, an Arrhenius base must have an OH minus group. Okay, so an Arrhenius base must be able to dissolve into an OH minus group. Okay, so something like KOH can dissociate into OH minus, so it is an Arrhenius base, and this also can accept an H plus proton, making it a Bronsted-Lowry base. However, something like NH3 is a Bronsted-Lowry base, but not a Arrhenius base because it doesn't have an OH group. Moving on to mono and polyprotic acid, you can break down the name and figure out that monoprotic means one proton. Polyprotic is many protons. Okay, so monoprotic acids are any acid that just has one H. So like we just went over, HCl, HF, all prime examples of monoprotic acids. Polyprotic acids just have more than one H. Polyprotic can be further specified into diprotic and triprotic. Di obviously meaning two, tri meaning three. Okay, an example of diprotic would be H2SO4. We got two H's there that it can donate. And we down here, triprotic, we have H3PO4, phosphoric acid, that can get rid of all three of those H's, making it a triprotic acid. This table here, just some common polyprotic acids. It's just helpful to become familiar with. Now we're going to move on to some molecular and ionic equations. So molecular equations are what everyone is used to. Okay, everyone is used to molecular equations. It's just the normal thing we've been getting in chemistry. Any sort of molecules coming together. Here, let me write a better one. Any sort of molecules coming together that are neutral and they have some sort of reaction. Okay, that is a perfect example of a molecular equation. That's it. That's all you need. It just needs to be balanced. Okay, that's balanced. A total ionic equation would be if I split each and every one of these molecules into its ions. The only thing you want to make sure you're doing when you separate these molecules into ions is you want to, for now, only separate the ones with AQ, aqueous, okay? Only separate the aqueous molecules. You never want to separate the liquid ones, and you never want to separate the solid ones. Those ones are going to stay the way they are, okay? So don't separate those ones. Spectator ions are things that don't change from products to reactants. Those will become easier to understand when we start going over them. And then net ionic equation is the total ionic equation just without the spectator ions. Okay, so we're going to go over an example of that right now. These are just some written down rules. If it's easier for you to understand the written down ones, feel free to pause the video, take a look at those. All right, so here we have your example. Okay, it's the same formula I wrote above. So the first thing we always want to do when we have these molecular formulas, okay, or equations, is you want to make sure it's balanced, okay? So take a couple seconds, make sure it's balanced. Okay, we'll come back. So it is balanced, okay? So now what you have to do, okay, you have to separate each and every molecule that has the aqueous thing behind it into its separate ions, okay? So HCl is going to be split into H plus and Cl minus, and both of those are going to be aqueous because they're in a solution, and Na it's going to be Na plus and OH minus, okay? And I'll show you what that looks like now, okay? So we have this HCl turns into H plus on the left and Cl minus, and then NaOH is Na plus OH minus, and then on the product side, NaCl turns into Na plus and Cl minus. However, H2O, because like we went over, is a liquid, we don't change that, okay? So now we have to go through and get rid of our spectator ions, and like I said, the spectator ions are something that doesn't change it doesn't change when you go from left to right. So prime example, Cl minus, okay? Cl minus and Cl minus. On both sides, it's Cl minus, okay? Doesn't change charge. And on both sides, it's aqueous. So nothing is changing from left to right. So it's not changing, so it is a spectator ion. Na plus is also the same thing, okay? Na plus, and it's aqueous on both sides, so it's not changing. So when we go to our net ionic, we're going to get rid of those, okay? H plus and OH minus will combine to make H2O liquid, okay? But that molecule here, this H2O molecule, is neutral, okay? So the charges are changing. This is going from H plus and OH minus to H2O neutral, so the charges are changing, and you're going from aqueous to a liquid, okay? So both its form and charge are changing. So those you're not going to get rid of. Those are not spectator ions. So you need to keep those. So you're going to keep those two. You can keep H plus, OH minus into H2O liquid. Okay, and that's all you have to do, okay? You're just splitting it apart, getting rid of the things that don't change, and then rewriting it in a nice, easy way, okay? So this is your net ionic equation. And this was my total ionic equation. Okay, so this was total before I started crossing everything out and got it all messy, okay? But when you have all these ions written out up here, that is your total ionic equation, okay? This is another example. If you guys would like to try it, feel free. The answer is here if you guys want to check your work. Just keep in mind, certain things changing due to how strong of an acid they are or how weak of an acid they are. Here we have our solubility table, okay? So the solubility table is a visual representation of the solubility rules. So the way you want it, and we'll probably be going over that in class in the future soon, but for now you just want to be able to make sure you can read this table and understand it, okay? So the soluble in water, the top part, it's telling you that all of these compounds here are usually soluble in water, okay? These first four here, the nitrates, ammonium salts, sodium, potassium, and ethanates, those are always soluble in water, no exception, okay? So if you ever see that sort of compound with a nitrate or something like that, you know it's going to be aqueous because it is soluble in water. However, the chlorides here, bromides and iodides, okay, those are usually soluble, but they have exceptions. When they meet silver, which is Ag, and lead, they become insoluble or partially insoluble, and then sulfates are the same thing. They have its exceptions. And then the bottom row, on the bottom here, I'm shading in right now, these things are all usually insoluble, but then vice versa, they have exceptions here that make them soluble.